Welcome back to Le Podcast de Philippe. We're going to be doing a deep dive into something kind of wild today. We're talking about a potential revolution in data storage.
Okay.
And I think before we jump into that, we need your help on YouTube to reach 1,000 subscribers today. We're so close. But what we're diving into is this idea of storing thousands of terabytes of data, like your entire digital life, on something the size of a coin.
Wow.
That's what scientists are exploring with crystals, doped with these rare earth elements. And we'll unpack how it works. The implications for fields like quantum computing and what it can mean for the future of data storage.
Sounds fascinating.
Yeah, it's pretty mind-blowing stuff.
It really is.
So, thinking about it, it's fascinating how our current storage technologies are being pushed to their absolute limits.
Right.
With just the explosion of data that we're generating.
Yeah.
SSDs and hard drives are great, but their density and durability
just can't keep up.
Which demands of big data and the ever-expanding Internet of Things. So how did these crystals address that? I read about this research at the University of Chicago using a specific type of crystal called praseodymium-doped yttrium oxide, or Euro. What makes them so special?
So the key lies in these tiny imperfections within the crystal structure called oxygen vacancies. Think of them as microscopic traps that can hold electrons. The presence or absence of an electron in these traps represents the ones and zeros of digital information.
So instead of magnetic fields or electrical charges, we're using the presence of an electron to actually store data.
Exactly.
That's pretty wild. How is the data written onto the crystal?
So they use light, specifically ultraviolet light, at a wavelength of 275 nanometers to trap these electrons. And what's remarkable is the power needed is incredibly low, about 5 microwatts per square centimeter.
Wow.
That's far more energy efficient than many of our current electronics.
Okay, so we use UV light to write the data by trapping electrons. But how do we read that data back? I'm assuming we don't just carry around a UV light reader.
No, you don't need a special UV light reader. The reading process uses green light, specifically a wavelength of 532 nanometers. This releases the trapped electrons. And as they are released, they emit light, a phenomenon called luminescence. This luminescence is detected and translated back into usable data.
That's so clever. But if these are just microscopic traps, how stable is the data? Could it be easily lost?
That's where the concept of shallow and deep traps come in, distinguished by their energy levels. Shallow traps have lower energy and can release electrons at room temperature, which means data loss is possible. Deep traps, however, have a higher energy level and hold onto those electrons much more securely, needing that specific green light stimulation for release.
So for long-term data storage, we'd rely on these deep traps within the crystal to retain the information?
Yeah, that's right.
That sounds like it could be way more durable than our current options.
It is.
What kind of storage capacity are we actually talking about? You mentioned something about a coin earlier.
Yeah, so researchers estimate a potential density of at least 200 million bits per cubic millimeter.
200 million bits in a space that tiny. So we're talking about potentially storing terabytes of data on something smaller than a grain of rice.
Potentially, yes.
What does this mean for something like data centers?
Well, data centers, as we know them, could be radically miniaturized. Imagine shrinking down massive server rooms to a fraction of their size with this technology. But it's not just about the storage capacity, it's also about the potential longevity. We could be talking about data storage that lasts for centuries, or even longer.
It's almost hard to fathom, this idea of storing massive amounts of data in a tiny, durable crystal that could potentially last for millennia is incredible.
It's pretty amazing.
But you also mentioned this technology having implications for quantum computing. I'm fascinated by that world, but honestly, it's a bit over my head.
Sure.
Could you shed some light on that?
Of course, so quantum computers are a whole other fascinating topic. At their core are quantum bits, or qubits, which are fundamentally different from the bits in our current computers. The challenge with qubits is their sensitivity to their environment. They are prone to losing their unique quantum properties, which is called decoherence.
So where do these crystals fit into the world of quantum computing?
These rare earth ions, like the praseodymium used in these crystals, are actually promising candidates for creating more stable qubits by controlling the charge environment around these ions, which is what this crystal technology allows us to do. We could potentially make qubits much more robust and resistant to decoherence.
So we're not just talking about better data storage, but potentially a key advancement in making quantum computers more powerful and reliable.
That's right.
That's a pretty significant implication. But let's be real. What are the potential downsides?
Well, it's important to remember this technology is still in its early stages. While the results so far are very promising, there are challenges to overcome.
What are some of those challenges?
One of the biggest challenges is the read and write speeds. While the potential density is impressive, the current methods are relatively slow compared to our existing storage technology.
I can see how that would be a bottleneck. If you're trying to access terabytes of data stored on a tiny crystal.
Absolutely. And then there's the question of long-term stability. While theoretically data could be stored for incredibly long periods, we need more research to confirm the practical limits and how factors like environmental conditions or radiation might affect the crystals over time.
So huge potential, but still some hurdles to overcome. But I think it's safe to say this could be a seriously disruptive technology.
Disruptive might be an understatement. Imagine the impact on everything, from personal devices to cloud computing, scientific research, even the way we archive information for future generations.
It's almost overwhelming to think about the possibilities, and perhaps even a little bit intimidating. What happens to the world when we have access to this kind of storage capacity?
That is a big question, and one that we'll need to grapple with as this technology matures. It's a powerful tool. And like any powerful tool, it can be used for good or for ill.
Well, this deep dive has given me a lot to think about. It's clear that the future of data storage, and maybe even computing itself, could look very different, thanks to these tiny but mighty crystals.
Yeah, definitely a field to watch closely. Who knows, maybe one day we'll be carrying our entire digital lives on a crystal keychain.
Now that's an image. Thank you for joining us on this leg of the journey as we've explored this incredible breakthrough in data storage technology.
It's been a pleasure. I'm excited to see where this goes.
Me too. It's pretty wild.
It is mind-blowing.
Yeah. All right, we'll be back in just a bit.
Sounds good. And it's not just about storing more. It's about how we preserve information for the long term.
Right.
Right now, we're constantly fighting against data degradation. You know, the slow decay of hard drives.
Yeah.
The limited lifespans of SSDs. Even cloud storage requires constant maintenance. And it isn't immune to failure.
It's true. We put so much faith in our digital storage, but it is inherently fragile in a lot of ways.
It is.
You mentioned that these crystals could potentially store data for centuries or even millennia.
That's right.
What are the implications of that kind of longevity?
It's amazing to think about. You know, imagine historical archives that don't deteriorate. Scientific data preserved perfectly for future generations. Even personal memories and records that could last indefinitely.
Wow.
It's a completely different paradigm for how we think about preserving our digital heritage.
It's a fascinating concept, but I have to wonder about the practicality. We've talked about rare earth elements, cutting-edge technology. The complexity of this research.
Right.
Wouldn't this type of data storage be incredibly expensive?
It's a valid concern. But remember that the amount of material needed for these crystals is minuscule. We're talking about packing an incredible amount of data into a tiny volume.
Yeah.
So even though rare earth elements can be costly, the cost per bit of storage could be surprisingly competitive, perhaps even cheaper than our current solutions in the long run.
That makes sense.
Yeah.
And we haven't even factored in the potential energy savings. You mentioned earlier how energy efficient the writing and reading process is compared to our existing technologies.
Absolutely. Think about the massive energy consumption of data centers today. This technology could significantly reduce that, making data storage not only more economically viable, but also more environmentally sustainable.
So let's say this technology really takes off. What would the transition look like? Are we going to be throwing out our hard drives and SSDs overnight?
It's unlikely to be an overnight revolution. As with any new technology, adoption takes time.
Right.
There will be years of research, development, testing, and refinement before we see widespread commercialization.
And I imagine there would be huge challenges in integrating this type of storage into our existing computer systems and devices.
Of course. It's not just about the crystal itself, it's about building a whole ecosystem around it. We need new interfaces, new protocols, entirely new software to harness the potential of this technology.
So it's a monumental task, but the potential payoff seems enormous.
Absolutely. It's not often that we encounter a technology with the potential to so fundamentally change how we interact with and preserve information. Just imagine the possibilities if we can overcome these hurdles.
It's mind-boggling to think about, but before we get too carried away with the future, let's come back to the present.
Okay.
We've talked about the incredible potential, but we also need to address the challenges and the potential downsides of this technology.
Yeah, you're absolutely right. It's important to temper our enthusiasm. with a healthy dose of realism. You know, this technology, while incredibly promising, does present some potential challenges.
Yeah.
And even risks that we need to consider carefully.
What are some of those risks? We've talked about the technical hurdles, but are there other concerns as this technology becomes more sophisticated?
One of the biggest concerns is the potential impact on privacy. If we have the ability to store vast amounts of data cheaply and for extended periods, it becomes that much easier for governments or corporations to collect and analyze personal information on a massive scale.
That's a sobering thought. We're already grappling with data privacy issues. In our current digital landscape, it's easy to see how this technology could amplify those concerns.
Exactly. It underscores the need for robust privacy protections and regulations to ensure that this technology is used responsibly and ethically. We need to be thinking about these issues now, before this technology becomes widely available.
Are there other societal implications we should be considering?
Yeah. Economic disruption is another major factor. If this technology truly revolutionizes data storage, it will inevitably lead to significant shifts in the industry. You know, jobs could be lost in traditional storage sectors, while new opportunities emerge in fields related to crystal-based storage.
So it's not just about the technology itself. It's about anticipating and managing the ripple effects across various industries and sectors.
Precisely. It highlights the importance of proactive planning and workforce development to ensure a smooth transition and minimize negative impacts on employment and economic stability.
It seems like this technology, like so many breakthroughs before it, presents a mix of incredible opportunities and complex challenges that we'll need to navigate thoughtfully.
It does. It's a reminder that technological advancements are never neutral. They are tools, and the impact they have depends entirely on how we choose to use them. This technology has the potential to transform our world for the better, but it also comes with responsibilities.
Well said. This deep dive has certainly expanded my understanding of not only the scientific potential, but also the broader societal implications of this technology. It's a fascinating and rapidly evolving field, and I'm eager to see how it unfolds. Thank you for guiding us through this exploration.
It's been a pleasure. It's crucial that we have these conversations and approach these advancements with a sense of informed curiosity and a commitment to responsible development. The future of data storage, and perhaps even computing itself, may very well hinge on these tiny crystals. And it's up to us to ensure that we harness their power for the benefit of humanity.
Couldn't have said it better myself. Thank you for joining us on the podcast, Philip, for this incredible deep dive into the world of crystal-based data storage. Remember to hit that subscribe button if you enjoyed the episode. And as always, keep exploring, keep questioning, and keep learning. Until next time.